Hello, welcome to Maths with EJD. Today, or in this video, I'm considering marginal distribution, and it is still under the idea of joint distribution. So it's closely related to joint probability distribution that was considered in the previous video. Simply, marginal distributions are derived from joint probability distributions, which describe the probability of two or more random variables occurring together. Occurring together. A marginal distribution provides the probabilities of one of these variables without considering the others. Essentially, so in quotes, marginalizing over the other variables. That is what they are called, marginal distribution. Okay, so there are two types, of course, as usual, based on discrete and continuous. So there are two main types of marginal distribution. So you have the marginal probability mass function. Because PMF there. And then we also have the marginal probability density function. PDF. Okay. So, of course, this is for, as usual, this is for discrete random variables. That's marginal probability mass function is for discrete random variables, while marginal probability density function is for continuous random variables. Okay. All right, so let's talk about how to find marginal distributions. So finding marginal distributions. First, we talk about the discrete random variables. So for discrete random variables, so to find the marginal distribution, of a discrete random variable, we sum the joint probabilities over the possible values of the other variables. So suppose X and Y are two discrete random variables with a joint probability mass function P of Px equals X, Y equals Y. Okay. The marginal probability mass function of X now, okay, is found by summing over all values of Y. For instance, we have the marginal distribution, marginal PMF of X equals X now is equal to summation over Y of probability that X is equal to X and probability and Y equals Y. Okay. So that's just how that is defined this way. Okay. Similarly, the marginal PMF, the marginal probability mass function of Y is probability that Y is equal to Y equals summation over X now of probability that X is equal to X and Y is equal to Y. Now, while this may be a bit hazy right now, with an example, the point can be driven home. Okay, so let's take an example to drive that point home. Okay, now consider the joint probability mass function for two random variables X and Y as follows. So we have probability that X is equal to X and Y is equal to Y equals, the probability is 0.1 if X comma Y is 0, 0. It is 0.2 if X comma Y is equal to 0, 1. Then it is 0.3 if X comma Y is equal to 1, 0. And it is 0.4 if X comma Y is 1, 1. Okay, so that's the probability mass function. So in this case, the marginal distribution of X is simply this probability. So the marginal distribution of X is probability that X, X can either be 0 or 1. Okay, so the marginal distribution of X now be probability X equals 0, for instance. That will be probability 0, 0. That means X is 0 and Y is 0, plus probability that X is 0 and Y is 1. Those are the two instances. And that simply means that, so probability 0, 0, we know that is 0.1, right? So that is 0.1. Then when X is 0 and Y is 1, that is 0, 1. So this, and the probability is 0.2. So that's plus 0.2. And the answer is, and when we sum all that together, that is simply 0.3. So the probability that X is equal to 0 is 0.3, because there are two instances when it's 0, 0 or 0, 1. Then we can also find probability that x is equal to 1. So probability x is equal to 1 would simply be probability that you have 1, 0 plus probability, or probability 1, 1. You know, or simply means addition. So when x is 1 and y is 0, you know, that's the probability is 0.3. So you have 0.3 here, plus when x is 1 and y is 1, from the PMF, when x is 1 and y is 1, we have 0.4. 0.4. And that probability that x is 1 is simply 0.7. Okay? So that's that for the marginal distribution of x. So the marginal distribution of y, on the other hand, the marginal distribution of y is following the same idea, probability that y is equal to 0. That is probability, whatever x is, we don't care. That's 0, 0 plus probability 1, 0. So when x is 0, y is 0. That's probability is 0.1, like before. 0.1 plus x is 1, y is 0. So that's 0.3. X is 1, y is 0. That is 0.3. And the total probability that y is equal to 0 is actually 40%. That's 0.4. And what about probability that y is equal to 1? Because that will be probability 0, 1 plus probability 1, 1. So probability 0, 1 from the PMF is 0.2. This now. So probability 0, 1 is 0.2. Then probability 1, 1 again is 0.4. So the marginal distribution of y in this case is 0.6. So you sum, so for x, you sum over y, for y, you sum over x. Okay, so now let's do the same for the second one, for continuous random variables now. For continuous random variables. So we've done for discrete random variables. So 2, you have for continuous random variables. Okay, so to find the marginal distribution, to find the marginal distribution of a continuous random variable, we integrate. Don't forget, for discrete, we always sum things up. For continuous, we integrate. So integration is like is analogous to summing up for discrete. So integration for continuous from random variables is analogous to summing up for discrete random variables. So we integrate the joint PDF, integrate the joint probability density function over the other variables, Okay. For instance, if x and y are continuous random variables with a joint probability density function f of x comma y, the marginal PDF of x is found by integrating over y, by integrating over y. So that means we have f of x equals integral from minus infinity to infinity of f of x y dy. So we are looking for x, but we integrate over y. So similarly, the marginal PDF of y, the marginal PDF of y is f of big variable, random variable y at a specific value y is integral from negative infinity to positive infinity of f of x, y over x. That's dx. Okay. Now let's take an example again to drive the point home. So suppose the joint PDF of x and y is given by f of x comma y equals summation x plus y if 0 is less than or equal to x is less than or equal to 1, then 0 is less than or equal to y is less than or equal to 1, and it's 0 otherwise, okay. So the marginal PDF of x is f of x, fxx is integral from 0 to 1, x plus y, the function itself now, between 0 and 1. Of course, anywhere, normally it should be negative infinity to positive infinity. So, okay, well, if I'm just going to, I just want to, do the normal thing, right? So normally this should be minus infinity to infinity. I won't do it for the other ones. So minus infinity to infinity of f of x, y, dy, right? But in this case, we should have integral from, so we should have integral, if you look at the interval now, so we only have x plus y defined for y from 0 to 1. So it means from minus infinity to 0, f of x, y, dy, plus 0 to 1, f of x, y, dy, plus integral from 1 to infinity, f of x, y, dy. So that's what exactly is happening. But because, this function is only defined, so the function is only defined for, it's only given as x plus y when y is from 0 to 1. So otherwise means below 0 and above 1, the function is 0. So it means that this goes to 0 and this also goes to 0. So in the long run, we have that f of x is simply integral from 0 to 1 of f of x, y, dy, and that is exactly what is happening. So, and that f of x, y is actually x plus y as given by the probability, the joint probability density function that is. So this is integral from 0 to 1 of x plus y dy. That is our f of xx. So in this case, now we are integrating just with respect to y. So x will be seen as a constant. So if you do that now, integrate x with respect to y, you get xy. And integrate y with respect to y, you get y squared over 2, or half y squared. And that is from y equals 0 to 1. I like to put this y to so that so to not be confused. So our focus is on y, not on x. So in this case now, even further, I like to do something like xy from y equals 0 to 1 plus half y squared from y equals 0, half y squared from y equals 0 to 1. So in this case, since y is the focus, you can bring out the x. So you have xy from y equals 0 to 1 plus half outside, then y squared from y equals 0 to 1. So you can now substitute for y. So you have x into, so better still. So when y is 1, you have 1 minus, when y is 0, you have 0 plus half into, when y is 1, you have 1 squared minus, when y is 0, you have 0 squared that way. So that means you have x into 1 minus 0 plus half into 1 minus 0 also. So that is simply x plus half. So it means that fxx is x plus half. So this is the marginal distribution of x. And this happens for when 0 is less than or equal to x less than or equal to 1. So that's our results. So this goes. All right. So for the other parts, we have just similarly, the marginal PDF of y is f of y, which is integral from 0 to 1 of x plus y dx. So you integrate over x now. So in this case, the focus is on x. So it differentiates x with respect to x. You have half x squared. Now the attention is on x, and this will be xy because y is now considered a constant. So that, and this is from 0 to 1. And just like what I did before, the focus is on x now. So you have half x squared from x equals 0 to 1 plus y outside x from x equals 0 to 1. And then you can have half into, when x is 1, you have 1 squared minus 0 squared, then plus y into, when x is 1, you have 1 minus 0, and then that is half into 1 squared is 1 minus 0 plus y into 1 minus 0. So that's simply half into 1 plus y into 1. And this is simply half plus y. And this happens so this happens when y lies between 0 and 1. So this is the marginal distribution of y. Okay, so of x rather, of x. And it's the marginal distribution of y. Yeah, marginal distribution of y. And we have integrated over x. And of course, y lies between 0 and 1. All right, so let's quickly talk about applications as this comes to an end. Applications of marginal distributions. Marginal distributions. So one application is you can use it to summarize joint distributions. Joint distributions. So marginal distributions provide a simplified view of complex joint distributions by focusing on individual variables. So if you focus on each variable, you can get some insight, which summarizes the joint probability distribution. Then it is also used for independence testing. Independence testing. So if the marginal distribution of a variable equals the corresponding conditional distribution, the variables might be independent. So that's one thing. So if the marginal distribution of a particular variable equals the corresponding conditional distribution, so you can say the variables are likely to be independent. So you use marginal distribution for independence testing. And lastly, we have real-world scenarios. We have real-world scenarios. So in a medical study involving two variables like age and blood pressure, the marginal distribution of age will tell you the probability of a person's age without considering their blood pressure. And of course, the marginal distribution of their blood pressure will tell you the probability of their blood pressure without considering their age. So something like medical study of age and blood pressure, or any two things you can take together. So with this, we come to the end of this video on marginal distribution. So if you have not subscribed to this channel, be sure to do that and hit the notification bell so you can always get alerted when a new video is released. And of course, don't forget to comment, like, and share so that more and more people can get to see this video and learn a lot more. Thank you so much for always standing by. See you.